mechanics involves some of the most counterintuitive logic in all of science. What I'm referring to is superposition, which is a property of quantum particles which causes them to only have a definite state after they've been observed. So I'll give you an example with position. So let's say this is the point of observation, that before this point, I don't see anything. So before it, we have a particle that's in all positions at the same time. Then after the point of observation, it's in one spot. Something that exemplifies this is the double slit experiment, where we have a laser which shoots at a spot equidistant between two slits in a wall, and then hits a light detector behind the wall. The result that we get is alternating light and dark waves, where the majority of the photons hit in between the two slits. And this is weird and shows something that's called an interference pattern, which is an example of superposition. So the only way to really represent a quantum particle state is to list all of the states that it could have after it's been observed, and their corresponding probabilities. It would be much easier mathematically if we can represent the true hidden state of the particle. So what we'll say is that the true hidden state of the particle will be a vector who has a magnitude, or norm, of 1. We'll call this vector the state vector, and all of the possible states that will be resultant after observation will be called projected vectors. And all the projected vectors will be orthogonal to one another. Orthogonal basically means perpendicular or at 90 degrees. The dimensions of our state vector will be equal to the number of projected vectors. We can use the projected vectors to approximate the value of the state vector, but we'll need a little bit more math before we do that. So first I'll define what a vector space is. It's just a collection of vectors which can be added and multiplied together. Some notable examples are R1 and R2. R1 is the real line, and R2 is the real plane. We say that R1 is a subspace of R2. We will define an inner product of two vectors, x and y, where x is equivalent to x1, x2, and y is equivalent to y1, y2. Then their inner product is just equal to the values of both of the vectors added together. We can define an operator as a matrix which we multiply by other vectors to get different vectors. So where v and u are two different vectors, a is an operator. If we multiplied a by v and we got v multiplied by some constant, lowercase a, then we say that v is an eigenvector and a is an eigenvalue. This a is an eigenvalue, and this v is an eigenvector. Eigenvectors with different eigenvalues are orthogonal, and every single eigenvalue corresponds to a subspace, which is a collection of all the eigenvectors with that particular eigenvalue. A projection operator is just an operator which projects a vector onto a subspace. So I'll draw a little graph here, and let's take a subspace such as this one right over here. We'll call this one L, and then we'll call this vector over here V. Then if we were to project V onto L, so we say P L V is equal to that vector there that lies along the subspace L. Vectors are the sum of their projections on the subspaces corresponding to the eigenvalues of some operator. So the discrete fundamental equation, or the discrete statistical algorithm, is PVAAI, where V is our state vector, A is a measurement, and AI is an outcome. Then we need to figure out how we can write this in a way that we can calculate it. So we know that a vector is a sum of its projections. So we'll define a projection for every single one of our eigenvalues or outcomes, AI. And we'll say that this projects onto the subspace defined by AI, which we'll refer to as LAI. Okay? Where uppercase A is an operator and lowercase AI is an eigenvalue. So if I were to draw an example on a two-dimensional plane right here, I'll define two orthogonal subspaces which correspond to LA1 and LA2, and I will define a vector, which is our state vector. Then I say that our vector is the sum of P A2V and P A1V. So what we get here is that using Pythagorean's theorem, the magnitude of V, which is equal to 1, is equal to the projection operator's magnitude squared, the projection squared, plus the other projection squared. So then, to answer our question from before, we find that AI is equal to PAAI squared, which is equal to the inner product of V with the projection. Wait, V there. And this is the complete discrete case. We call it discrete because we have a finite number of dimensions. When we work with an infinite number of dimensions, we'll call it continuous. Now, when we have an infinite number of dimensions, we won't necessarily have eigenvalues. So no eigenvalues. None of that. So instead, we'll define delta to be a real interval and we'll define a subspace corresponding to delta called LA delta, which is equivalent to all vectors V such that PVA delta is equivalent to 1. So it's all vectors that produce a value within delta with certainty all the time. So then we can find a projection operator onto our subspace called PA delta, and then we get the fundamental equation of quantum mechanics, which is PVA delta equals the inner product of V with PA delta V.